All right, this is homework to part three, and it is October 7th, 5:30 in the afternoon. Starting from a force balance on a cylindrical controlled volume with either a pressure drop or vertical elevation, show that the fanning friction factor uh, is equal to 16 over the Reynolds number for laminar flow. Uh, for this homework, we're going to be doing the elevation drop method. I listed some equations that we need just in case I get stuck and need to reference back. Those would be the flow rate Bernoulli's equation, the shear stress equation relation to the shear rate and the viscosity, the frictional heating coefficient relating to the fanning friction factor, and the Reynolds number. So, starting off here, we have our cylindrical control volume. Acting on this volume, we have the force of gravity and a shear stress. We also have an inner radius and an outer radius, along with height delta z. So let's create a force balance. The first force we have is the force of gravity, which is the rho times the volume times gravity. So we're going to have rho times the volume, so that is pi r squared times the height, and then times gravity, plus the shear stress, 2 pi delta z is equal to 0 because it is a force balance, it must equal to 0. We can now cancel some terms here. Delta z cancels, pi cancels. I'm sorry, I'm missing an r here. The r cancels, which leaves us with rho g plus shear stress 2 times the shear stress. It's equal to 0. Now the shear stress can be rewritten as viscosity times the shear rate. The shear rate can be rewritten as dV over dr. So we can rewrite this as 2 over mu times dV over dr. Let's get dV over dr by itself on the left-hand side. dV over dr is going to be equal to the negative rho g over 2 mu. Now, if we integrate an indefinite integral, we can solve for the flow rate here, or the solve for v. So v will be equal to negative rho g. Missing an r. I am missing an r. Missing an r. Rho g over 2 mu times r squared over 2 plus c. Now we have the c value and we have to solve for it. We know that when r is equal to r, big R, that v is equal to 0. So we can plug that in. The mu r squared over 2 plus c, which means that c would be equal to c would be equal to positive rho. So this is positive. Rho g big R squared over 4 mu. Now again, when r is equal to big R, that means the flow is 0 because they would be the same width. So if we plug that back in for v, we would get v is equal to rho g rho g over 4 mu. Big R squared minus R squared. Just double checking real quick. Making sure I'm not missing anything. I am not at this time. So the next thing we need to talk about is the flow rate. The flow rate is Q is equal to velocity times the area. The flow rate can be rewritten as flow rate is equal to the integral of B times the differential area. We'll be using the differential area because we'll be using the Shell's method. So that is 2 pi r. So the flow rate will be an integral from 0 to big R of rho g over 4 mu times r squared minus r, big R squared minus r squared, times 2 pi r dr. We can then pull the constants out rather. That'll be rho g 2 pi, we can get rid of this 2, so rho g pi over 2 mu, integral from 0 to big R, of r, big R squared, little r squared, big R squared r minus r cubed, dr, when we take the integral, excuse me, it'll be Q is equal to the same thing. That will be r, big R squared, little r squared over 2 minus r to the 4th over 4 from 0 to r. Now when we solve for that, it's just big R, so it will be Q is equal to pi over 2 mu of big R squared over 2 minus big R to the 4th over 4, which will just simplify down to this will just be 2 pi over 2 mu times r to the 4 over 4. We can put that in. A mu. Now we know that r, big R, is equal to d over 2. So since it is to the 4th, when we plug this in, it is going to turn out that rho g pi d to the 4th is equal to 128 mu. So the next part we need to talk about is the Bernoulli equation. Which is equal to P2 minus P1 over rho plus V2 squared minus V1 squared over 2 plus G delta C is equal to the negative frictional heating constant Velocity doesn't change, and the pressure doesn't change. So the only thing that we need to take into account here is these factors: frictional heating constant, gravity times the height. We actually can put our flow rate in terms of gravity here. So we'll do that really fast, and then plug it into this equation. So that'll be G is equal to 128 Q times mu over rho pi d to the fourth. We can then plug that into the equation, and we will get 128 Q over mu times delta Z is equal over rho pi d to the fourth is equal to the positive frictional heating coefficient. It's the positive heating coefficient because I remember. I think it's due to the fact that the force of gravity is down. It's flipped for some reason. I forget what the reason is. That's bad on me, but I should know. The frictional heating coefficient is positive in this case. If we remember from lecture, the frictional heating coefficient can be related to the fanning factor. That is 4 times the fanning times delta x over 2, and then d squared over d. I wrote it up here. Let's check and see if that's right. Look at that. It is right. Let's just flip. I flipped these two, but it doesn't matter. Beautiful. So we can relate this equation to what we just found with the fanning factor. We can cancel some things. We can cancel delta x and delta z because they're basically the same thing. We can cancel all of this. This will be 64. We'll get rid of one of these. So we'll have 3. And then we'll multiply the v squared over, velocity squared over. So we'll be at 164 q mu look at the top of the bottom. Look at the top. Actually, like at the bottom. Is equal to rho pi over dq. This v goes down to the bottom. Make sure we're not missing anything else. All right, so we know that the Reynolds number is equal to remember from lecture, the Reynolds number is rho Vd over mu. And we know just from looking at this that we are nowhere near there relating, because we're trying to find that 16 over the Reynolds number is equal to the fanning factor for laminar flow. But we also need to remember that Q is equal to V times pi d squared over 4. So if we plug that in, V pi d squared over rho pi dv squared, and we cancel and simplify this. We just have 1. This is 1. This cancels. 64 divided by 4 is 16, which leaves us with 16 d mu, over I messed this up again. This is d cubed down here, so this is going to be e to the 1. So this is 16 mu over rho vd equal to the Fanning factor. And if we remember, Reynolds number is rho vd over mu. This is the inverse of Reynolds number, which is 16 over the Reynolds number. So this, in fact, is 16 over the Reynolds number. And that is exactly what we want for our final answer. We found that the Fanning friction factor is equal to 16 over the Reynolds number for laminar flow. Little rundown again of what we did. We started with a force balance. We found our velocity value right here. We then used the flow rate equation and integration with shells to find the flow rate. What the heck? We then used the flow rate to solve for gravity, to plug into the Bernoulli equation to relate the frictional heating coefficient. We then use the relation of the frictional heating coefficient with the Fanning factor to solve for the Fanning factor relationship to the Reynolds number. Thank you very much.